All right, welcome back. I made some changes to the course. Instead of doing 8 sections in chapter 14, we're only going to do 7 sections. And then that way we could finish up. I want to try to finish up this week, if not by Saturday or Sunday. That way it'll give you all of next week to finish the homework assignments, practice, and take all the exams, and give you enough time to try to finish everything by the Saturday following. All right, so hopefully we can get everything done this week. All right, today we're talking about chapter 14, section 6, tangent planes and differentials. All right. So it's a continuation of Calculus 1, Calculus 2. We know that a derivative is the slope of a curve at a point, or rate of change. Rate of change. We also know that the slope is of the tangent line. Will this be last week? Well, I'm going to try to finish up all the lectures, but I'll still meet with you all next week if you have any questions. But yeah, because we only have 16 sections and we're finishing up chapter 14 today, tomorrow. And chapter 15 only has 3 sections. Chapter 16 has 3 or 4 sections. So we may go into Monday of next week, but as you know, next, Tuesday is the 4th of July, and a lot of y'all we're doing celebrations and stuff. So that's why I'll know there's going to try to finish up so you guys don't get bogged down. You just have fun with your families. All right, thank you. So the derivative is the slope of a curve at a point. The slope is that of the tangent line. To the curve at a point. All right, so again, that's what we learned in Calculus 1. The function, in order to have a derivative, it's got to be differentiable, and it still exists now. It's got to be differentiable. It's got to be continuous at every point in the domain. So we're starting off looking at tangent lines, or tangent lines in 2 dimensions, and then we'll go to tangent planes in 3 dimensions. So tangent lines, the reason we use that or allow us to linearize a function. At that point. This is called linearization. In this section, we're going to see how the gradient, remember that's the del operator, defines the tangent plane, because now we're dealing with 3 dimensions. And now to deal with 3 dimensions, we're talking about a level curve or a level surface. Of a differentiable function. Now we'll see how the gradient defines the tangent plane to a level surface of a function at a point that's on the surface itself. So as above, this tangent plane will give us the linearization of our function at any point. Okay, so that's what we're going to try to do in this section. All right, so the first part. Because you can see your homework assignments deal a lot with this. We're going to deal with tangent planes and normal lines. I remember when I first learned calculus, I thought normal lines, that looks like a good line. That's a normal line. But then I realized that when we talk about normal lines, we talk about orthogonal or perpendicular lines. All right. In section 5, we looked at how a function of a smooth curve on a level surface where f is differentiable everywhere. It gave us this function. So the partial, the derivative of our function with respect to t we're looking at the function of a smooth of the derivative of the function with respect to a smooth curve is equal to the del of our function at the derivative. The rate of change of that, or the velocity vector. Or remember, r s represents the arc length, r represents the speed, the rate of change, the movement of on a smooth curve, r prime is the velocity vector that defines it. Okay. Also, okay, let's just get r is defined as all right. So it says that since it's differentiable, since our function is differentiable, on the smooth curve, r, then the derivative of this function is 0, because this is your vector at a function, gives us a point along that curve at whatever point we're looking at. So the derivative of that will give us 0. And the gradient, the right-hand side of f of our function, is orthogonal or normal to the curve's velocity vector, r prime. All right, so, and this is what we did last time. Let's look at now curves. Passing through a point on the curve. So our earlier equation tells us that all velocity vectors all our vectors at p sub 0 are orthogonal to our del operator at that point. So what that means is we have our curve. All right. There's a point P on that curve, P sub 0. There's a tangential plane on that touches the curve at that point. So any velocity vector we pick, these are all velocity vectors, are going to be orthogonal to our del function. All right, so what that means is because this curve is a flat plane, the velocity vectors are on that plane. and they're normal or orthogonal to the del function is orthogonal to those points, as it's just set up here. The gradient of the del function is orthogonal to the velocity vectors. That's what that means. Let's define what we mean by tangent planes and normal lines. The tangent plane to a level surface, which is any function that we're given, equals, because remember, level surfaces, this is the beginning of the chapter, level surfaces is where the function equals a constant. And f is differentiable. Tangent plane to a level surface fx is equals c, where, I should say, where f is differentiable function f at a point p sub 0. So this is a tangent plane. So we get a level surface. It's differentiable at a point where the gradient is non-zero. The gradient is non-zero. So the tangent plane to a surface is non-zero. So the tangent plane is the plane through that point and orthogonal or normal to the del of that function at our point p sub 0. So given a level surface fx xyz equals c of a differential function f at a point p sub 0, where we have a non-zero gradient through a point p sub 0 and normal to 0. So that's what the tangent plane defines. Yeah, and that's going to be one. We've seen that formula before. We'll get to that in a second. We've discussed this, but indirectly. The normal line is the line that goes through our point and is parallel to our del operator at that point. You say on the surface of the smooth curve, or a smooth curve. So the normal line is parallel to the operator, and the tangent is orthogonal or normal to it. These work I'll define the following hold when the gradient at some point p sub 0 is a non-zero vector. So tangent plane to some function equals c at p sub 0. This is the formula we'll use. The partial of f at our point and the difference, x minus x sub 0. The partial of y at p sub 0, y minus y sub 0. And the partial of z, z minus z sub 0. All that equals 0. So this is the formula we'll use whenever we're finding the tangent plane. Yeah, it's got to equal 0 because we're looking at the orthogonal function to it. And the normal line to our function at a point is our initial value x. Each of these are parametricized. So our x value is x sub 0 plus the partial derivative of f at x at our given point times t. Y is the initial value plus the partial with respect to y at the point p sub 0, t, and z is equal to the initial, the z value of our point, the partial with respect to z at our point, t. So these are the formulas we'll be using almost exclusively in this and pretty much the next section also. Example 1. Find the tangent plane and normal line of the level surface x, y, z equals x squared plus y squared plus z minus 9 equals 0. At our point, this is our point. All right, so again, once you see it wants a tangent plane, we know from there that our formula has to be our tangent plane formula, which we just talked about. Set it equals 0. All right, so what we have to do now is first of the steps. Find the partial derivatives of f of x, f of y, f of z. So our partial of x is just 2x. Partial of y is 2y. And the partial of z is 1. Now the second step, find those values at p sub 0 at our point 1, 2, 4, because we have to define what these coefficients are. So it's 2x is 1. That equals our partial of x. 2 times 2, which is 4. That's our partial of y. And 1, that's our partial of z. And x sub 0 we know is 1. Y sub 0 is 2. Z sub 0 is 4. Sorry about that. My dog is outside chasing the gardeners. All right, so now we defined f of x. So now plug and play. So f of x, x minus x sub 0, f of y, y minus y sub 0, f of z, z minus z sub 0 equals 0. So the partial of f is 2. X minus the x sub 0 value is 1. Partial of y is 4. And the y sub 0 value is 2. This is x plus the z sub 0, f of z is 1, and z sub 0 is 4. All right, now what you do is distribute and group. So we have 2x minus 2 plus 4y minus 8 plus 1z minus 4 equals 0. So we have 2x plus 4y plus z, -10 minus 14. And so we have 2x plus 4y plus z equals 14. So that's the tangent plane to our surface. All right, now the second thing we have to find is the normal line to the surface at PO. At our point P sub 0. And that is this simply this parameterization, x sub 0 f of the partial of x at our point t, y is the partial of y at p sub 0, oops, y sub 0 plus partial of y at our point t, and z equals our initial plus the partial at t. X sub 0 is 1. Our partial of x at our point is 2t. Now our y value, our initial value for y is 2. That's the point we're going through. The partial of f of y is 2 times t. No, 2 is 4. I'm sorry. F of y is 4. And z, initial value is 4 plus 1t, or just t. And that's all there is to it. And whenever our homework assignments, well, that's the same thing. It's just repeat that process. Oh, also, if you're given this function z is equal to f of xy, if you're asked to find the tangent plane to a smooth surface, z is equal to f xy at some point p sub 0, which is at and the first thing you have to do is has set equals 0. The reason to do that is because it's a non-zero level surface. Where the non-zero level surface is this is x, y minus c, because this is a function with 3 variables. So the partial derivative of our function, or derivatives. So partial of our function with respect to x is the partial of our function with respect to x Remember, it equals this whole thing. That equals, remember, z is a constant, so it equals partial of our function with respect to y with respect to y. This is partial of f with respect to y, partial of z. And lastly, with respect to z, the partial of f of xy is 0, partial of z is 1. So those are the partials whenever you're given an equation, z is equals cosine f of x or xy or something like that. So if z is defined as a function of x and y itself. The formula we just had, again, it's taking a p sub 0. P sub 0 equals 0. Remember, this defines the tangent plane to the smooth surface at our point, p sub 0. So the partial of capital F is so if you look what just happens here, that's a partial of y at our point. And the partial of z is f z at p sub 0. Then we do the same thing. It's as long as, remember, as long as it's non-zero vector. If it's zero vector, then not much we can do with it. The plane tangent to a surface at some point but remember, this one, in this section, we're going to talk about when z equals fxy. So that's why our major function, our capital function f, is with these three variables. So if we're given this definition as this just proves, what we have here is our function, partial function at our initial values. The partial with y at our initial point. Minus z because remember we have z is equal to f of xy. We set them equal to 0, so we put the z at the end and find the partial derivatives from there. Find the plane tangent to the surface, the smooth surface, x cosine y minus y e to the power x at our point 0, 0, 0 at the origin. All right, so the first thing we have to do, because remember our formula is, we have to find the partials of f and x. So at our point. So the partial, I should just write that. It'll save us lots of time. So the partial of derivative of x, in this first part, is x goes to 1, so it's cosine y. The derivative of x here, e to the power x is 1, e to the power x, so it's y e to the power x. At our point. So we have cosine of 0 minus 0 times e to the 0. Cosine of 0 is 1. 0 e to the power is 1. So it equals 1. The partial at y with y. So x is a constant, leave it alone. Cosine of y, derivative of cosine is negative sine. And derivative of y is 1. At our point. So we have negative 0 sine of 0 minus e to the power 0, which is 0 minus 1, negative 1. So the not equation just yet. So the plane tangent f of x, x minus x sub 0, f of y, y minus y sub 0, minus c minus c sub 0. So that's 1. X minus 0. That's negative 1. Y minus 0. Just plug in the values. Distribute. Yeah. Let me rewrite this so I'll get rid of the other page. Distribute. And you see, so we have x minus y minus z equals 0. And there's your solution. example 3. Now we have two surfaces. X, Y, Z, F is x squared plus y squared minus 2 equals 0. Then we have second surface at x plus z minus 4. All right, so what we have to do here is we have to find our parametric equation. This is a cylinder. This is a plane. There's no exponents. The surfaces meet in an ellipse E. Find parametric equations for the line tangent to E at the point 1, 1, 3. Sorry. All right, and here's where we start different approaches to what the book has and what I'm going to show you how to do. I think it's a lot easier, less work. But let's look at what this one says. So the surfaces F and G meet in an ellipse. Find the parametric equations of the line tangent to E at the point 1, 1, 3. So the tangent line that is normal or orthogonal and parallel to our vector V. This is what we have to find. So the first thing we have to find are the del operators. At p sub 0 or 1, 1, 3. Remember, the del of f is the partial of f x I and f y j. So the partial of f with respect to x at the point p0 I, partial of f with respect to y at the point p0 j. So the partial of the original function, x squared plus y squared minus 2 with respect to x is 2x I at 1, 1, 3. The partial with respect to y is 2yj at 1, 1, 3. 2 times 1i, 2 times 1j. So the partial of f is 2i plus 2j. Do the same thing with g. At 1, 1, 3. The partial of g at the point p0i. The partial. Oh, yes, we have k here, so we have partial with respect to y, j, partial with respect to z, k. Remember, g is equal to x plus z minus 4. So we have the first and third. So the partial of x is 1 at our p sub 0, which is 1, 1, 3, I. The partial of y is 0 since it's a constant, j. And the partial of z is 1 at 1, 1, 3, k. So it equals to I plus k. Just 1. So that's our del G. Our vector V is the cross product of f and g, which means we have to find the determinant. Or discriminant, I mean. So the first one is 2i, 2j, 0k, 1i, 0j, 1k. Determinant of V is I, j, k, and repeat the first two columns. 2, 2, 0, 1, 0, 1, 1, 0. Add these products. 2 times 1 is 2i plus 0 times 1j plus 0 times 2k. Now we subtract these. Minus 1 times 2j minus 0i minus 1 times 2k. So 2i, that 0, that 0, that 0, minus 2j minus 2k. Remember this at the point 1, 1, 3. And we were asked to find, what were we asked to find? Find the parametric equations of the line tangent to E at that point. So So we have to parameterize E at the 0.113. So X is equal to X sub 0 plus V at 113 T, Y 0 plus 113 T, Z is equal to Z sub 0 T. So our X equals, our X value is 1. The I component is 2 T. Y sub 0 is 1. The J component is 1. No, the J component is negative 2 T. Z sub 0 is 3. The K component is negative 2 T. That's how we find those. All right, next section, next part of this section deals with estimations. Estimating change in a specific direction. So up until now, we're just saying that here's a point. Now it's like a change. Whenever we're talking about change in a specific direction, we're looking at directional derivatives. Remember, directional derivatives is just that it's a vector. It's a derivative that points us in a specific direction. How does this play in effect? It's the same as it is in anything else, as with ordinary differential equations. It's used when we want to estimate how much the value of a function changes if we move a small distance ds. From point p sub 0 to another point, we call it p sub 1. In calculus 1, when we deal with single variables, we had the derivative of f is the derivative at our original value times the change. This is the change, sure. This is a small amount. This is one variable. Since if we deal with two variables or more variables, then we're talking about the del of the function dot u times the direction, the small change, the movement. Remember, this we defined last section as the directional derivative. And this is your small change. Remember, u is since it's a vertex, it's the direction of motion. From our point P. Let's look at a specific one. Estimating the change in our function in a specific direction defined by our unit vector u. So our derivative of the function is, as we just said, our del of f dot. Remember, whenever we have a dot product, it becomes a scalar. All right, let's look at an example here. Estimate how much value of our function y sine x plus 2yz will change if the point p sub 0 moves 0.1 units. No, that's just point. That's a point. We're moving from our original. Straight toward p sub 1. Estimate how much the value of our function y sine x plus 2yz will change if our point moves 0.1 units 0.1 units from the initial value 0, 1, 0 straight, because remember, we could move in curves, so we have a sine cosine as our functions as well. So the first thing, since it's moving from to someplace, we have to find the derivative of f at our original point. In the direction of the vector p sub 0, p1. That's where it's moving. Let me see. 0, 0. Yeah, okay. Remember, we found those. We take our values 2 minus 0, 2 minus 1, negative 2 minus 0. So x2 minus x1, y2 minus y1, c2 minus c1, ijk. Okay. Second step, we have to find the magnitude of this function. Because we have to define what u is. 2 squared plus 1 squared plus negative 2 squared, 4 plus 1 plus 4 equals 3. Find u. So we take each of those, we get 2 over 3i plus 1 over 3j minus 2 over 3k. So that defines our u. Yep. We have to find our delta function from our original point. So that's the partial at p0, the partial of y at p0, ijk, so we have to find f of x first. So our function, let me write the function down here again. Y sine x plus 2yz. So the function with respect to x, that's a constant, so derivative of sine is cosine. So it's y cosine x. Those are constants, disappear. Now the partial with respect to y, sine disappears, so it's y plus y disappears, so it's 2z j. And with respect to z, that's a constant. So with respect to z, it's just 2y. That is our del operator. Now we're going to take the dot product. Write that out. So no, we're not done yet. So we have to figure out what this value is at 0, at p sub 0. So at p sub 0, it's 0, 1, 0. So 1 cosine 0 I, 1 plus 2 times 0 j, plus 2 times 1 k. Cosine of 1 is 1, so it's I. Plus with respect to y. Oh, that's just sine. I'm sorry, that's not y, it's sine. So sine of 0. Sine of 0 is 0, 2 times 0, so it's 0j. So it's I plus 2k. That's our del operator. The derivative of x is y cosine. Derivative of y is just sine x, 2z. And derivative of z is just 2y. Yeah. So now we do a dot product of those two functions. Sixth step. It's I plus 2k dot u is 2 over 3i plus 1 over 3j minus 2 over 3k. This one is really I plus 0, 1i, 0j plus 2k. Because when we do the dot product, just coefficients. 1 times 2/3, 2/3. 0 times 1/3 is 0. 2 times negative 2/3 is negative 4/3. 2/3 minus 4/3 is negative 2/3. All right, so now we have that dot product. Now we're going to look at with respect to the change. P1 to P, or P0 to P1, or P1, P2. I forgot what I named those. 0.1 units. From P sub 0 in the direction of U. So the derivative of f is equal to del f dot u times the small change. So we had u is negative 2/3 times 0.1 equals negative 0.066666666, which is 67. All right. Again, we've known how to find del f. We know how to find u. We know how to find the dot product. Just multiply by whatever change we have. Okay. Let's look at how do we linearize a function with two variables. This adds a new dimension of difficulty because we sometimes like trying to figure out what the derivative of sine x over x as x approaches 0. We have to use an approximation of another function. All right, so here where we have, let me see. Okay, so suppose we have z equals f of xy. And it's near a point x sub 0, y sub 0. Function of f must be differentiable so since f is differentiable, it's continuous everywhere, then we could find f at x sub 0, y sub 0. We can find the partial derivative of x at x sub 0, y sub 0, and the partial derivative of y okay, so as it moves in both the horizontal and vertical directions by delta x and delta y increments. Again, delta x, actually the delta function is the second point minus the first. But since we only have one fixed point, in y minus y sub 0. So if it moves in both horizontal directions, we move by delta x, delta y increments. We then get the function that defines its movement as the original function minus a function remember, this is the y value. These are the y values. The partial of f with respect to x at the original value times the increment of change, the partial of y at the original value times the increment of y plus these small movements or epsilon 1 and epsilon 2 are small increments that tend to 0 as delta x and delta y go to 0. What we're looking at here is an extension of the first derivative rules we learned in Calculus 1 using the epsilon delta proofs. So as our function moves, has a rate of movement, and as long as epsilon is the distance, as long as x and y, x1, x2 are not the same, but as x1 approaches x2, or x2 approaches x1, we get to a limit point. So this is, in essence, what we're looking at here. So this gives us this approximation. It's an approximation. So we have our original function plus the partial at the original times delta x is x minus x0 plus the partial of y at our initial point that's the linearization of our function in two variables. We start off with our initial point, and then these are the direction. This is the directions and the amount that we move. Eventually, as x sub 0 and x become the same value, those go to 0, and we get to our final location. Okay, so let's define linearization. the linearization of a function f xy at a point p sub 0 where f is differentiable is the function linearization xy, the original function at our starting point plus our change. Remember, we begin at f of x sub 0, y sub 0. We get this approximation. So our final value, our final function, is approximately the linearization of our function. It's called the standard linear approximation of f at a point. And it's actually, this part of the function should look pretty familiar. It's literally what we've been doing. The derivative with respect to x times change of x. Beginning minus the end minus the beginning. So let's look at an example here. Find the linearization of our function f of xy, or x squared minus xy plus 1/2 y squared plus 3 at 3, 2. Since we're looking for the linearization, let's write down our formula. So in order to find the linearization, we have to find 3 things. We need to find f at our initial point, which is 3, 2. We have to find the partial of x at the point 3, 2. And we have to find the partial of y at the point 3, 2. So the original function at 3, 2, we get 3 squared, 3 times 2, 1/2, 2 squared plus 3. 3 squared is 9. 3 times 2 is 6. 1/2 times 4 plus 3. That becomes a 2. So 9 minus 6 is 3. Plus 2 is 5. Plus 3 is 8. Now the partial derivative of x. So we have 2x minus y at 3, 2. So we have 2 times 3 minus 2. 6 minus 2 is 4. So this is f, this is fx. Now the partial with respect to y, which is negative x 1/2 2y. So it's negative x plus y. X is 3, y is 2, is negative 1. All right, so now we have those parts, plug them into our equation. So the linearization at our xy, notice we can't put 3, 2 here because 3, 2 was original starting point. So f of xo, yo to x minus x0 plus fy at 3, 2, y minus y0. So we get f at the original point is 8. F of x is 4. X minus 3. And then f of y is negative 1. Y minus 2. Distribute. We got 4x minus 12. Negative y plus 2. We have 4x minus y minus 2. So that's the linearization at the point 3, 2. Again, the question is, still depends on the accuracy. So how, remember it's an approximation. So how can we minimize all this? By approximation an upper bound. An upper bound for the magnitudes of our double second derivative and are mixed. On our rectangle R at that centered point. So if we could find those, then we could find the error throughout all of R. The error is simply found by the difference of our 2 points. The error to our in the standard linear approximation. That's an oops. This depends on if f being differentiable has continuous first and second derivatives or partial derivatives. Throughout R at x sub 0, y sub 0. If f being differentiable has continuous first and second partial derivatives and m is an upper bound with the values on R. So if all this stuff is true, then the error at x at some point that we got in replacing our function on the domain by L. In other words, this. Satisfies our error function. So by replacing f of x with this function, we can satisfy the error plus or minus, that's where we get absolute values. It's less than or equal to 1/2 m times the sum of the absolute differences. The reason why we take the absolute values is because it can have a positive or negative value. If it's negative, it makes it smaller. When it be larger, and we square that value. Again, we can change these. By choosing a different final point. Because you start off with x and y, x sub 0, y sub 0. And the closer that we pick x and y to x0, y0, the smaller the error is going to be. So there's our error. Let's look at now differentiables. Okay, now what is a differentiable? Again, differentiable simply means that there's a difference. X minus x sub 0, y minus 0. There's a delta function going on here. Let's look at single variable first. So in calculus 1 in algebra, we define y equals f of x. So the change in f occurs when we change or move from a to from a point from number a to another one, a plus delta x. I could put x and x here. So the delta f would be the a plus delta x minus, that's how we defined our limit function. Let's try two variables. We have a function now. Again, f is differentiable, which means partial derivatives exist in R. So as we hear, we move from x to x plus delta x. Here we move the change in f occurs when we move from xy to x, or some initial point, x sub 0 plus delta x, y sub 0 plus delta y. And that can be represented as this: f x sub 0 plus delta x, y sub 0 plus delta y, minus f of x sub 0, y sub 0. Now, how we write this to our linearization, yeah, all the stuff is related back to what we did in calculus 1 to find for derivative. We took the difference quotient f of x plus h minus f of x over h. It's practically exactly the same process. So the change in the linearization of our function occurs when we have that change. We define delta x as x minus x sub 0, and delta y is y minus the original value. Then the change in L becomes x sub 0 plus delta x, y sub 0 plus delta y, minus L x sub 0, y sub 0. And this, in essence, becomes the partial of f at our original point times delta x plus the partial of y at our original point delta y. Okay. So the differentials change of x and the change of y are independent variables. So they can be anyhow you want them to be defined. Where d of x is the same thing as delta x, which is, if you think about it, this is exactly what we had when we talk about derivative. It's a change of position. Here's a definition. If we move from our initial point, x sub 0, y sub 0, we'll call that point 0, to point 1, which is at to a point, let's call it p sub 1, which is at x sub 0 plus delta x, y sub 0 plus derivative of y. The change becomes the differential of f, the derivative of f, is the partial of x at our original point, dx, plus the partial of y at our original point, in the linearization of F. This is called total differential of F. So if we move from initial point to another point nearby, okay, you start with x of 0, you move some delta x points. The change becomes from f of x, f from f at some point xy to these new points, the partial derivative of f at the initial point times its change, that's the horizontal change, and then the vertical change, partial of f with respect to y times the change dy. Example 6. Suppose a cylindrical can is designed to have a radius of 1 inches and a height of 5 inches. But the radius and height are off by the amounts of dr equals positive 0.03 and dh. So the change in the radius is 0.03 inches and the change in the height is off by negative 0.1 inch. Estimate the resulting absolute change in the volume of the can. Okay, suppose a cylindrical can is designed to have a radius of 1. Radius of 1 and a height of 5 inches. But the radius and height are off by estimate the resulting absolute change in the volume of the can. So the first thing we have to start off with, since we're looking at the volume of the can, is we have to know the formula for the volume of a cylinder. Pi r squared, which is the area of a circle, times the height. So to find the change in that, we're looking at dV, which is the partial of r at our initial height and radius times its change, and the partial with respect to the height of the initial values times its change. So the partial with respect to r comes 2 pi rh. The partial with respect to h is pi r squared. 2 comes down, we have pi. So we get our difference in V becomes VR, which is 2 pi RH dr. Well, let's put those in there. So I put those in first. What is dr is 0.03. Negative 0.1. Okay, now with the values. So the initial values is the radius is 1, height is 5. 2 pi times 1 times 5 plus pi 1 squared negative 0.1. 5 times 1 is 2 times 1 is 2 times 5 is 10. So it's 0.3 pi. 1 squared is 1. So it's minus 0.1 pi. So dV becomes 0.3 pi minus 0.1 pi is 0.2 pi. 3.14 times 0.2, 0.28 inches cubed. So volume, since we're dealing with volume, it's inches cubed. So there's our solution. Let's take another example. Example 7. Your company makes stainless steel right circular cylindrical molasses containers or storage tanks that are 25 feet high with a radius of 5 feet. How sensitive are the tank's volumes to small variations in height and radius? Let's look at this. Molasses containers that are 25 feet high. The radius is 5 feet. Again, we're looking at the volume, which is essentially doing with cylinders, pi r squared h. And we're looking at the change of volume. So we look at for the VR and then VH. Of course, at the original information. So VR is 2 pi RH, VH is pi r squared. So 2 pi RH at hour point 225 dr pi r squared dh. 2 pi r is 5, h is 25. Pi 5 squared dh. 2 times 5 is 10, so it's 250 pi dr plus 25 pi dh. So what this one says here, for every 1 unit change in R, the volume changes 250 units. Likewise here. For every 1 unit change in height, the volume changes 25 units. Or 25 pi units. Okay, so far we've limited ourselves to X and Y. It would limit ourselves with 2 variables. So functions of more than 2 variables. Let's look at the 3-dimensional functions. Similar changes as before. The linearization of X, Y, and Z now at point 0, this is X0, Y0, Z0, is this. We start with the original function at 0, then the partial of x at p0, x minus x0, plus the partial of y at p0, y minus y0, plus the partial of z at p0, z minus z0. We'll just add another dimension to it. Okay, now here's where the bigger one changes. Remember, we're dealing with rectangular solids. So our error function, we have absolute value of f of xx, f y y y, f z z, f x y, f x z, and f of y z. All right, actually, this should be the other way around. So then the error becomes the error x, y, and z is the function x, y, z minus linearization of x, y, z. And it's roughly about, again, all this stuff is going to be squared. We have the magnitude of x minus x sub 0, plus the magnitude, the absolute value. We just add the third dimension in there. The only real big problem was with these. The difference with delta differentiation, or differential. The f becomes f of x at p0 dx, partial of y at p0 dy, plus partial of z at point dz. That's the approximation it gives us. It just adds, again, it's the same as we did in the past. If we go from 2 to 3 to 4 to 5, it just adds one more dimension to it. The only problem comes with the error. Example 8. Find the linearization L x y z of the function x y z equals x squared minus xy plus 3 sine of z at the point x sub 0, y sub 0, z sub 0, 2, 1, 0. Find an upper bound for the error incurred in replacing F by L on the rectangular region. So these are our bounds, our limits with respect to our inputs two. So find the linearization Lxyz of fx x squared minus xy plus 3 sine z at the point 2, 1, 0. Because this one here was z minus z sub 0. Since that was 0, we just had z. Find the upper bound of the error incurred by replacing f by L on the rectangular region. So the first thing we have to do is find F210, the partial at 210, the partial of y at 210, and the partial of z at 210. Those we have the linearization. So our function again is x squared minus xy plus 3 sine z. So we have 2 squared minus 2 times 1 plus 3 sine 0. 4 minus 2 plus 0 is 2. The partial, first off, the partial here with respect to x is 2x minus y. At 210, we have 2 times 2 minus 1. 4 minus 1 is 3. With respect to y, that goes to 0, so we have negative x. So it's negative 2. And with respect to z, derivative of z is 1, so derivative of sine is cosine. So it's 3 cosine of z. Cosine of 0 is 1. The answer is 3. Okay, so let me see what I have here. Our f function is 2. F of x is 3. Fy is negative 2. Fz is 3. Well, we have to find the linearization. That's what fx. So this becomes 2 plus 3, and the point was 2, 1, 0. Distribute 3x minus 6 minus 2y plus 2, 3z plus or minus 0. 3x minus 2y, 3z. 2 minus 6 is negative 4. 2 plus 2 is 4. So it's minus 2. So our linearization is that. Oop, that's step 2. Find linearization. Just step 3. Since we have x, y, and z, we have to find xx, yy, cz, xy, xz, and yz. So fxx, we go back here, f of x, take this derivative again. That equals 2. Fyy, the derivative of y with respect to that is 0. And z, derivative of z is 1. Derivative of cosine is negative sine, so it's negative 3 sine z. Okay, now we're going to find xy. So remember, when we read those, we read those backwards. We're doing xy first. So since we did the x first, we now take derivative of this function with respect to y. Then we do xz. There's no z or x in there, so it's 0. And there's no y in there, so it's 0. All right, so that probably is the longest part. Oh, I see what page back. We're looking at the error. Find the upper bound for the error incurred by replacing f by f on the rectangular region. All right. And what was the last one? F of z. That's 0.01. And looking at those, if it was 6, we make it 6. If you look at this, look at the second derivatives and look at the largest value, because that will be the upper bound. So with this, now we go up here. M is 2. What are my values? Oh, there they are. We have absolute value of x minus 2, y minus 1, and z minus 0. Or so these errors in the rectangular region were defined. X minus 2 is 0.01. Y minus 1 is 0.02. And z minus 0, which is just 0, is 0.01. Those cancel. 0.04 squared, which equals 0.0016. Right, that about does it for that section. All right, thank you, everybody. I try to have these posted ASAP. I'll have the homework assignments also posted for chapter section 7 as well. And we'll do the notes. I'll do the notes and send those to you too. All right. Have a good day, everybody.